Okay, good morning, good evening, good afternoon. At some point, someone is going to have to teach me how to say these things in your language. But for now, I hope that what I'm saying is understandable, and it looks like you did very well on exam one, but there are a few corrections. So for today, I'm going to show you the correct answers and how to get them. So here we go. Exam 1, review. Good job on this question. The key here is to look at heat. The other thing that we're looking at in this case is mass, and we're also looking at temperature. So we have heat, we have mass, and we have temperature. And this is a little bit of a preview for 102, for exam number 2, and I'll show you a new equation right now that you haven't seen before. This will help to help you think about energy, mass, and temperature. So give me one quick second. I'll be right back. Okay, so in the last lecture, we talked about the relationship between power, energy, and time. Remember, power, energy, and time. In this very first question, which you got right, and I'll show you a couple more, we're talking about heat, mass, and temperature. And I'm going to bring up one equation here for you. Heat, mass, and temperature. So what I'm showing you is the thermal heat. So Q is energy. C sub P is heat capacitance, mass is mass, which we measure in pounds, and delta T, this is one single variable. So this is heat. The C sub P is heat capacitance, H-E-A-T, capacitance. Mass is, well, it's just mass, and we measure this in pounds, or kilograms, and then finally this is temperature. Okay, so I hope you can read this. Okay, so again, heat, this is Q is heat, and heat is energy. Heat and energy are the same thing. Heat is thermal energy. Okay. C sub P is heat capacitance. Now, if we go back to the screen, water, we're looking at water here. Water has its own heat capacitance. And let me show you how to find that, because we typically deal with water. Heat capacitance of water. Okay, so here's the number right here, 4.4 joules. See, there's joules there. And if you remember from last time, joules is a measure of energy. BTUs is also a measure of energy. Two different versions, just like kilograms versus pounds for mass. Okay, so joules for energy. Gram, of course. Gram, we can see, is a unit of mass. So pounds per kilogram. And then finally, the last one is temperature. And temperature can be measured in degrees Fahrenheit, degrees Celsius. And we'll do a little bit more on units later, but that's what we're talking about. So again, heat is energy. Heat capacitance, water has its own heat capacitance. Everything around us has mass, except for light. Light does not have mass. And again, mass can be measured in pounds, also kilograms, or just grams. See the G? That's the letter G, 1 gram of water. And then finally, temperature can be measured in Fahrenheit or in Celsius. It can also be measured in Kelvin or Rankine. And we'll talk about Rankine last time. Okay, so good job on question 1. I think we're starting to understand thermal energy or heat. Okay, so then this next one, I don't think we really covered this, but let me just show you what this means. So this is a good guess. This is a good guess to look at how quickly something is used. So if you said, if I'm spending money and I have maybe $10 and I spend $1 every day, then in 10 days I have no more money. It's the same way with coal and oil and natural gas. But in this case, the correct answer is the RP ratio. So R is the reserves and the P is the production. So let me show you how this works. It's very similar to the same as how money works or spending. So I'm going to draw a little figure. I'll show you. Okay, so now we're going to cover the reserve production ratio, this RP ratio that you missed. And here, I don't think I explained this before, so here we go. So here's two different ways of looking at this. We can see that this is the entire reserves from 0 all the way up to the top, or over here 0 to the top. And you can see that the reserves are the same. There's the same amount. So let me show you. With 2 glasses of water, you can see that the reserves are the same. Both glasses start off full, all the way to the top. Now, if I take the one glass and I drink very fast, I went down by 1/5. Or I can go very slow and say, oh, just a little bit. Now let me draw that. In the first case, I had a lot. Sorry, I had 1/5. In the second case, I had just a little bit, 1/10. So in the first case, we could just say RP equals 1/5. Or in the second case, we can say RP equals 1/10. So 1/10 versus 1/5. So in the first case, I'm consuming very fast. 1 day, 2 days, 3 days, 4 days. I'm all gone in 5 days. Too fast. Or RP10, 1/10, 2/10, 3/10, 4/10, 5/10, and the supply lasts longer. That's the RP ratio. Okay, that's the second one. And I think you know that the second one is better. It's better to consume it slowly. It lasts longer, more sustainable. Okay, so question number 4, you also got wrong. I'm a little disappointed. This one you should have gotten right. So the question says oil, wind, coal, and electricity are the 4 dominant forms. Well, it's a little bit of a tricky question, so you almost got it right. It's okay. It's okay. What you should know is that oil and coal are the primary dominant forms. And maybe this question wasn't so good, but let's just do a little bit of research and clear it up. It's okay. I don't think I asked the question quite right. It's my fault too. It's my fault. It's not a very good question. But let's look. Let's look. Okay. So here is world energy consumption, and what we can see here, oil is the main one. Coal is also quite high, but decreasing. You can see that coal is decreasing. Gas is also quite high. So renewables are quite small. And also you can see that nuclear is shrinking. So inside of renewables are also wind. Another thing to examine here is worldometers. This is a website, so if you look up here at the top, it's worldometers.info, and you can see that this is all of the energy used today. This is what's used today from non-renewables, so mainly coal, oil, gas, solid, liquid, and gas. Those are the three primary forms. And only about one-fifth or so is from renewables. But that percentage is changing. We will use more and more renewables, and that's the point of this course. Okay, so that's okay. We got that one right. This, of course, is false. Good job. We know that as the population increases, we use more and more energy. And that's also shown on worldometers. So let's look here. We can also see that the number of people is always increasing as well. One second. So here you can see that as the population increases, energy consumption also increases. And I don't know, these guys are the fossil fuel guys, and I'm not sure I like their advertising on this site. Oh well. Oh well. Okay. So that's quite good. So question 5 is good. Question 6. Which of the following statements is incorrect? So let's take a look at this one. This one's not very easy, so let's just take a look here. Give me 1 second. Okay. So the next question, question 6, says which of the following is incorrect? So the right answer is this. So let me just show you how this answer is actually correct. I think you know that's incorrect versus correct. Okay, so let me draw another picture here. So if we have 1 ton of oil, 1 T-O-N-N-E, 1 ton, that's the British, that is 1,000 kilograms of oil. Okay, we'll start like this, nice and neat. 1 ton, it's a large amount, 1,000 kilograms, and now we set it on fire. All right, so we light a match, and then the oil is set on fire for whatever, for heating, for our automobiles, for electricity, what have you. That is correct. That is 1 ton. That is the amount of heat released. So when you burn 1,000 kilograms, that's the amount of energy in that ton. So 1 metric ton oil equivalent is that. But now that actually is correct. What you selected was a correct answer, which in this case is wrong. So now let's go and look for the one statement that is in fact wrong. Okay, so if we go here, 1 ton, so we're going to go to 1 ton of oil equivalent conversion. All right, so 1 ton of oil equivalent equals 4.1 times 1087, 4.187 times 10 to the 10th joules. Okay, so that's the same. So 1 ton of oil has that much energy. Now let's write that out scientifically. Okay, so 1 metric ton oil equivalent equals 4.187 times 10 to the 10th joules. Okay, so here we go. So this is 1 metric ton oil equivalent. So that's, again, that's this barrel of oil. That's how much energy that has. That equals, it's the same, that equals 4.187 times 10 to the 10th joules. Now I'm going to rewrite that. Okay, equals 4.2 times 10 to the 10th joules equals 42 times 10 to the 9th joules equals 42 gigajoules. Okay, now let's just take a look at this. So what I did first, I came here and started with the original from the screen. I started over here on the website. Started over here on the website with the conversion. And then I went from there and I estimated, I just rounded. I said that 4.18 is approximately 4.2, and then I had 10 to the 10th, that stayed the same. Now I moved my decimal. I went from 4.2 times 10 to the 10th equals 42 times 10 to the 9th. So see that? 4.2 times 10 to the 10th equals 42 times 10 to the 9th. I just shifted my decimal, right? Okay. And then we also know that 10 to the 9th is giga. 10 to the 9th is giga. So 10 to the 3rd is kilo, mega, giga. 3, 6, 9. Kilo, mega, giga. So 10 to the 9th is giga. So we go back to our problem. This one is also correct. That's correct. A ton of oil equivalent would meet the energy demands of 40 average Americans. That's about right. So that also means that 40 people burn about that much oil per day. That's also correct. But this top one is incorrect because it says 4.2, and we know, of course, it's 42. So 4.2 gigajoules is the only wrong answer. Okay, that was a good one, and I got to say, that's a very important skill to have when you're doing your calculations. You need to have these math skills in order to get all of your photovoltaic problems correct. Okay, let's look at problem 7 now. Okay, you got that one right. One of the difficulties in interpreting energy statistics at the international level. So in this case, we're asking every single person in every single country to add up all of their energy. Very hard problem. Lots of people, lots of countries. It says all of the answers given are factors that contribute in difficulties in collecting statistics. So sometimes we say we consume energy. So if are we consuming this energy right now? Or is I producing it? So my body consumes it, the glass produces it. What's the difference, right? Okay. Disagreements over the heat content of an energy source. It's true, because sometimes wood will have some energy, oil will have some energy, gas, and different types of fuels will have different energy densities. That's also a problem. Difference in conventions regarding the reporting from power plants. Sure, so sometimes a certain amount of energy will go in, a different amount of energy will come out, and that's also hard to measure. Okay, so good job. Which statement is incorrect? A kilowatt hour is 3.6 gigajoules. Good job. That's very good. We calculated last time that it's 3.6 megajoules. So very good job there. That's very important to get those. Nice. Okay. Now let's go through these guys. I think question 9 you got everything correct. Let's just straightforward numbers, memorization. Very good. Question 10. Let's go to question 10. Carbon dioxide is released only by human processes involving consumption. No, this is not correct. So even right now, as I breathe, I make carbon dioxide. If we have a forest fire, that's carbon dioxide. There's or decaying matter. There are a lot of natural processes that create carbon dioxide. Okay, this one is question 11. Question 11 is very important. Okay, so let's review that one because we already did the BTU. Now we'll do the calorie. Okay, and I think if we go back to that water page, we'll find that. If we go back to that water page, let me find that again. Okay, so the next question, I think maybe I had an error here, but let's just go back and look at the definition. So the amount of heat energy, we're on question 11, the amount of heat energy to raise 1 gram of water 1 degree Celsius. Let's go out here and look at this. So you are in fact correct. So let's 1 calorie. Let's go here. 1 calorie. Yeah. So right here, the small calorie or gram is the approximate amount of energy needed to raise 1 gram of water 1 degree Celsius. So yes, you're correct. And I guess that's 1 calorie, and we write this as 1 C, and note that's a little c, 1 calorie. So one gram of water is about that big. It's just 1 centimeter by 1 centimeter by 1 centimeter. And if we go, let's just say from 20 degrees C up to 21 degrees C, that requires 1 calorie of energy. So that's correct. And just to be complete, we can do a few. So if we say, let's go from 1 calorie, it's also sometimes said as 1 gram calorie. That's the same as 4.18 joules. We know that. And we can do a few other calculations as well. We can put that in kilocalories, obviously 0.001. Doing that calculation, we can go in watt hours. We can change from any type of energy to a different type, just like changing from one type of money to a different type. So let's go back and look at this equation. So 1 calorie is correct. You could also say this is the same as 1/1000th of a kilocalorie. You could also say this is 4.18 joules. You could also say 0.0011 watt hours. Okay, so those are all correct. And I think maybe that might have been my error, but energy to raise 1 gram 1 degree Celsius is in fact 1 calorie. Okay, good job on that. Okay, so moving right along here, question 12. good job. You got that one correct. So hydropower, as we know, when water falls, first of all, water goes up because the sun comes down and creates enough energy to make water turn from liquid into vapor. And then, of course, when the water gets high in the air, there's no longer energy and it forms rain and comes back down. So hydropower, as we see right here, hydropower is an example of solar power. Hydropower is solar power. Wind, also, as you said, what makes the wind blow is so when the sun comes down and hits land here, it becomes warm. And if the land is warm, it makes the air warm, which makes the air go up. And when air goes up, it forms a circle, and this is what makes wind. So the hot sun makes the land hot, makes the air hot, and creates wind. So wind is also from solar. Waves on the ocean are just created from wind blowing across it. So of course, wave is also solar. Oil is from the remains of plants and animals that have gone underground and decayed for a long time. All of the oxygen is gone, and so oil is also an indirect result of photosynthesis, which we discussed last time. And then geothermal is very different. Geothermal does not come from the sun. Geothermal comes from the fact that long ago the earth came together by colliding bits of mass and chunk, and all of those collisions created energy. So we've got this very hot core, and that heat slowly comes to the surface, and that's all just based on friction and collisions from long ago, about the same time that the sun was actually forming. So good job on question 12. Very good. Okay, question 13, it looks like we got this one wrong. Now let's look at a kilowatt, because we did cover a kilowatt last time, and I'm going to go find my notes. Give me one quick second to find my notes. Let's just start at the beginning. And we know that energy is power times time. One thing we did not discuss specifically, and here's another way to look at energy, is that for potential energy, so let's look at this. So if I'm going to take, again, this glass, and I'm going to raise it from here to here, that takes energy. It takes energy because I'm pushing it, push, right? So that took energy to do that. And another way to express energy is potential energy. So E equals M, so M for mass, times G for gravity, times H for height. So let's think about this. So anything has mass. So this is kind of heavy. This pen is very light. So the glass has more mass, and the pen has less mass. So the more mass I have, the more energy I have. So that's mass. Now for gravity is always pointing down. So remember, if I'm standing on the earth, there's a certain amount of gravity. If I'm on the moon, there's less gravity, so I weigh less. So the amount of energy to push something up depends on where I am. If I'm in outer space on a spaceship flying around, there's zero gravity, so it's very easy to push things. And then finally, height. It takes more energy, so to go from here to here is a little bit of energy. To go from here to here is more energy because it's more height. So this is true. a rate of conversion to lift 100 kilogram person 1 meter in 1 second. So let me show you. So if I have equals 100 kilograms, 100 kilograms, right, times gravity, which is 10 meters per second squared, times height, which is 1 meter, equals 1,000 kilograms times meters squared over seconds squared equals 1,000 joules, right? Now, if I do this in 1 second, if I do it very quickly, I know that power equals energy divided by time. Power equals 1,000 joules per 1 second equals 1,000 watts equals 1 kilowatt. Pretty cool, huh? Okay, so I'll review that one more time. So we went back to energy equals power times time, or power equals energy divided by time. So we went back to our first notes. And this is also, what we're seeing here, this is potential energy. Potential energy. Sorry, I'm writing so slow. It's because I don't have my special pad. Potential energy. So again, this energy is mass times gravity, which always points down, times height, which goes up, and that's potential energy. So I have 100 kilograms, and if you want, you can go and stand on a scale and see how much you weigh. Maybe you weigh, gosh, I don't know, 40 or 50, maybe 60 kilograms. That's your mass. This is gravity, and we make it approximately approximately 10 meters per second. It's actually 9.8. We multiply that by 1 meter, and we end up with this is gravity here again. This is our mass. This is our gravity, and this is our height. We multiply them together. 100 times 10 is 1,000. The kilograms come over here. Meters times meters is meters squared, divided by seconds squared. And so this is the definition of a joule. 1 joule is 1 kilogram times meters squared divided by seconds squared. That is 1 joule. And then we go back for power. Power is energy divided by time, and we go from joules per second into watts, and that is in fact 1 kilowatt. So that is correct. A kilowatt is also 1,000 joules per second. We know that's correct. This is also correct. And we also know that kilowatts are SI units. So let's just review SI units for a little bit here. SI units. International units. Okay, so the standard is a meter, a kilogram, and a second. So kilograms, meters per second are also SI units. So kilogram, meters, seconds, and we go to NIST. These guys are very good. They make the rules. This is a very good page to have, physics.nist, and we can see there's the meter for length, kilogram for mass, seconds for time, and when we combine those together, meters times seconds squared kilograms times meters squared divided by seconds squared, that's 1 joule. Meters squared times kilograms divided by seconds cubed, that's a watt. I'll write that down. It's very important. This is actually very, very important. Okay, 1 joule equals 1 kilogram, 1 meter squared over 1 second squared. 1 watt equals 1 kilogram times 1 meter squared over 1 second cubed. Okay, so look at this now. Okay, so that's 1 joule on the top, so 1 kilogram times 1 meter squared divided by 1 second squared. 1 watt is 1 kilogram times 1 meter squared divided by 1 second cubed. Energy, power. Power is energy divided by time. That's where that extra second comes in. Very important. Okay. Okay. 14. Let's look at 14. Though difficult to quantify according to author text, blank is understood to be the total content required, embodied. Okay, so here's where I'm going to show you. I'm going to show you chapter 1. I'm going to show you chapter 1 of the textbook, and I'm hoping you can go into the Moodle shell and read this. So I'll show you the textbook right now. This is very important. Here's the text. And so this is the book that we use. This is the book we use for my students, and I'm happy to share it with you. Okay. Energy and Sustainable Systems. This is chapter 1. Okay. So this is world primary energy consumption. World primary energy consumption. Okay. So if we look at this chart, we can see we have biomass. So biomass would be trees, plants, anything that's living. That's why it's green. Coal is also primary energy. It's the Earth is not making any more coal. We are burning coal much faster than the Earth can make it. So that's also primary energy. Oil the same thing. That's primary energy because the Earth is not making oil anymore, or it's making it so slowly, much more slowly than we burn it. Same with natural gas. It's been in the ground for millions of years. Hydro and wind, kind of small here, but that's also energy that's all around us as primary energy. And then nuclear energy also. Nuclear energy has been here since the beginning of the Earth. So those are all primary energies. Something that is not primary energy would be electricity. So when we put up our solar panel, we go from solar energy into electricity. Electricity would be secondary. Or if we had a battery, which was chemical, that would be secondary. So these are all primary energies. And again, we can see these as all primary. You'll notice that electricity is not listed here. And you can see that over time, the as these other non-renewables came online with coal, with oil, with natural gas, the percentage of renewables has dropped, but it's flattened and it will rise. It will rise again. Mark my words. That's why we're here. Okay, let's go back. Okay, so primary energy is the answer there. Okay, now this is also very important. When we consume energy. Now remember, I have some water in this class. When I drink the water, I consume the water. All right, so the water goes into my body. Now, the first law of thermodynamics. Let's go there. Let's go to the first law of thermodynamics. Wikipedia is good. Wikipedia is good. Let's see. I need a picture. Let's try it again. Let's try this. Images. Oh, this is terrible. This is no good. Well, this is okay. This is okay. It just says that the energy before and after are always equal. Whatever I put in, I'm going to get out. But it might just be a little bit different. Just a little bit different. So I can either go from, and I'll just list out the different types of energy. And I have a good video on that. Let me show you. There's a good video.
Oh,
Okay,
I don't
let's
have
just watch
energy
this.
to work. I don't have ability to work. I'm tired.
Yes, you're right. Energy is ability to work.
Energy is ability to do some work. Do cars also use energy?
Yes, they use petrol or gas as energy. So, petrol or gas
Chemical.
is energy which make things to move. All things
Chemical
require
energy.
to move.
So we can store energy?
Yes, energy can be stored, like in the petrol tank of a car.
All things need energy to move.
Moving is kinetic.
Is stored.
Kinetic energy. Kinetic.
Oh, I used so much force and energy, but very less work was done.
Yes, Jenny, you applied a lot of force and you used so much of your muscular energy, but you could only move few things. Hence, less work was done. Now we would see different types of energy.
Oh, this bulb is
Oh,
giving so
light
much
energy.
of light.
Yeah, it works on electric energy.
Electric energy.
Electrical energy? Hey, this fire is giving so much of heat.
This is called heat energy.
Okay.
Heat energy? Okay, tell me, what energy is this?
You're doing work with your muscular energy.
Muscular
I don't
energy?
like that. Chemical and kinetic.
Oh, it is so hot here.
You know where heat is coming from?
Yeah, I know. It is all coming from the sun.
Yes, you're right. Energy which comes from the sun is called solar energy.
Solar energy.
You know, this bulb in night does not need electricity. You see that panel?
Yes.
It stores solar energy
That's
during
not
the
correct.
day from sun, and at night it gives that energy to the bulb.
Oh, so this bulb works on solar energy.
Let me show you something.
Hey, water has so much force.
Oh, this is energy of water which moves things.
This is called water energy.
Yeah, this is called hydro energy because water is also called hydro.
Hydro energy. Oh, these are big fans.
These are called windmills. They produce electricity.
Hey, listen. Wind helps in electricity also.
This is called wind energy.
Wind energy. Hey, listen. It's getting so windy.
Let's go home.
Okay, so that was almost right. Not quite right. Not quite right. But let me show you some other. Let me show you some other examples. Okay, this is better. This is much better. So, kinetic energy means something moving. That's kinetic energy. Potential energy, that's what we saw before. So here's to go up. Potential energy. Mechanical energy is both. It's kinetic plus potential. It's both together, mechanical. Electrical, we covered that last time. That's volts times amps. Magnetic, if you have a magnet, it can pull something towards it. Gravitational is gravitational. We can think of gravitational as the same as potential. So if you have gravity, you can have potential energy. Chemical energy is, like they said, muscle. Chemical is muscle, and chemical is also like in a battery. Ionization, that's very, very small. If you have, it's also similar to chemical ions, ionization, the very small level. Nuclear energy is from, well, maybe you know nuclear power plants where you have uranium that degrades and becomes thermal. Chromodynamic, that's with physics, we won't worry about that for here. Elastic energy is if I pull something, like a spring, or I bend it like this, that's elastic energy. Mechanical wave energy it's also elastic, it's just moving. Sound, of course, sound energy we know. Radiant, that's solar, same as solar. Radiant is solar energy. Rest energy, that's E equals mc squared. Rest is similar to nuclear. Rest is similar to nuclear. And then thermal, that's what we just did. We did thermal already with the, this was our, oh, sorry, 1 second, thermal. This was thermal. remember, so this is thermal energy. Okay, so those are the types of energy. So to get back to our question, we convert energy from one form to another. We use it up, and work is done. So when we so A, C, and D. Oh, I see. This is yeah. Okay. Okay. This is not a very good question. I'm sorry. This is not a very good question. Yeah. This is correct. All right. This is correct. This is not correct. And this is not correct. It's correct. That's usually correct. So when we do work, I take energy and lift. So I'm using energy to do work, to push, like the boy in the video. This is so if I take my phone, this is doing work. I use energy to do work. So that's also correct. Okay, that's a tough question. That was kind of a hard one. All right. 16. In general, what is the average efficiency of most combustion engines? No, it's maybe 30%. So what that means is 30% does work, 70% is heat. Let me show you. Okay, now I'm showing you Chapter 2. This is Chapter 2 from the textbook. So if I have 260, this is coal coming in. A lot of it just goes as heat. Some of it then goes to steam, then it goes through a cycle, and only 100 comes out. So let's do this. So if we have 100 divided by 260 equals 38%. That's actually pretty good. We can see down here with hydro is usually much more efficient. So 20% would be a little too low. Okay. Question 17. Blank is the capacity to do work and is measured in joules. That's correct. That is correct. Oh, good job. Question 18. Very good job. Yeah. The power is the rate at which work is done, and of course this is equals energy, not power. Very good. Good job. Okay. Question 19. Greenhouse effect. This is correct. Very good. Question 19. Of the 5 largest consumers, which has the worst consumption to production ratio? Oh, okay. Let me, I'll show you a table. Let me show you a table. Let me show you a table. Okay, so now we're looking at, again, we're looking at the RP ratio. Remember this? It's the RP ratio. Okay, so if we go here, let's look at comparisons. Population, energy produced, energy consumed. 1 second. Okay, so here we go. So if we look at the questions, we can see that we have Sri Lanka, US, Japan, Korea, Australia. So this is consumption to production ratio. So if we do it for the United States, let's just go back here. The United States, production to consumption. Production to consumption. So we have production is 14.8 produced divided by consumed is, so divided by 19.3. 76, so the U.S. is 76% efficient, I guess you'd say. Let's look at Japan. 0.8 divided by 4.3 equals, only 20%. Let's look at India. 3.8 divided by 5.2 equals 73. Pretty good. Okay, and then the other one, I think Sri Lanka is not there, but Korea, Australia, they're not listed. But actually, from this chart, it's Japan. Japan is the worst. So this is relatively large and relatively small. You can see Canada produces more than it consumes. Same thing with, let's see, it's consumed. Canada, yeah, Canada produces more than it consumes. The UK, wow, produces more than it consumes. Australia produces more than it consumes. So Japan has the worst. Japan is the more energy comes into Japan on a ratio than they export. Okay. Okay, question 21. A ton of coal. So again, ton of coal, this is the same as our oil. So remember, ton of coal, we could also just have, instead of coal, we could have big black coal, 1 ton, fire. So again, if we have one ton of coal and we set it on fire, then that's how much energy is in that coal. It's also 28. Okay, so right here, coal, it's chemical energy, 26 to 33. Very important to know. So we can see here's ethanol, coal, methanol, and this is one of my favorite figures. This is one of my favorite figures right here. It's kind of hard to see. Come on, come on. Let's try again. Energy density on Wikipedia. Let's go. Come on. Okay, come on. Much better. Much better. Okay. anthracite, and here is bituminous, and this is megajoules per kilogram. And so the question said 28 gigajoules per ton. So this is megajoules per kilogram. We can see anthracite, yeah, it's about 30. Bituminous, yeah, maybe 24. So let's do the math. Let's do the math here. So 28 megajoules per kilogram equals 28 gigajoules per 1,000 kilograms, and that's the same as 28 gigajoules per metric ton. So 1 metric ton. Metric ton, 1,000 kilograms. Okay, that's good. That's good to know. Very good to know. Very good to know. And also TCE is tons coal equivalent. Okay, so all of the answers are correct. Insert, check mark. Okay, question 22. We're getting close to the end now. Question 22. This is good. 1 calorie and 1 calorie. Very good. Both correct. Good job. And that's also a kilocalorie. Or 1 kilocalorie. Very good. All right. Geothermal energy is always defined as a renewable source because the supply of heat from the earth can never be exhausted. At a particular location. Okay, this one is interesting because in geothermal you can have some hot water here, but if I pull it very quickly, it's gone. You can it's like right. So geothermal, maybe I have. You know, in my geothermal, I can think of the water as energy, right? So maybe geothermal comes in like this: drip, 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 drip. But if I go like this, it's too fast. So it can be exhausted. Geothermal can be exhausted, at least in a local spot. Okay, problem 24. 24 is very tricky. Very tricky. It's bad professor making a tricky problem. B is correct. It's not wrong, but C is more correct. So the way the sun works, it's the gravity, all the gravity from all the gas pushes the hydrogen together. The gravity causes the fusion. Now this is not correct because fission, this is only with heavier elements. Fusion right? So fusion is pushing together, fission is coming apart. So fusion, I'll show you. Fusion is hydrogen plus hydrogen becomes helium plus energy. Fission is uranium becomes other elements. Plus energy. Okay, so the top, this is fusion. Fusion is two hydrogens, so hydrogen plus hydrogen becomes helium plus energy. So this is fusion, and the bottom one is fission. Uranium becomes other elements plus energy. So let me show you my other favorite. Dynamic periodic table. Very good. Okay, so if I have, so hydrogen comes together to form helium. So H plus H becomes He plus energy. That's fusion. To get fission, we have to go all the way down here. This is uranium. And what happens in the sun, you get enough fusion, and eventually you make iron. And when you make iron, all of the fuel is gone. Same thing if you're doing fission. All of these elements split apart, and once you get to iron, all of the nuclear energy is gone. Iron is a very special, Fe, iron is very special because you get fusion, 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 fusion up to iron, or you get fission, 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 fission down to iron. Okay, that's a good lesson to know. Whew, there's a lot in here. Okay, we are just moving along. Question 25. Kilowatt is a unit of power. Kilowatt hour, unit of energy. Perfect. Very good. What type of energy meets over 30%? Oil. Crazy, but true. Okay, ladies, thank you very much. I really appreciate your attention, and I will see you for another Skype, and then we'll cover the materials for 102. So we just finished 101, all of the primary energy, all of the conventional energy, and now we'll move into 102, which is renewable. And I'll show you what we just finished. I'll show you what we just finished. Boyle. These are the two books. Okay, this is for 102. So that's renewable. That's Boyle. And let's do another one. So Everett, okay. So Everett, there we go, Everett is 101, and Boyle is 102. Okay, so this is to keep in mind. We just finished Everett, which is 101, and now we're going to do Boyle, which is 102. Okay, so again, this is 101, orange, that's Everett, and you can see fossil fuels, dirty, right? And here is Boyle, renewable energies, very clean. Okay. Again, thank you, and I'll see you tomorrow morning.